Okay. Just to recall what we did in the last class, towards the end, we considered one periodic sequence, where when one period you have value 1 at n equal to 0 and otherwise all zeros, and that got repeated. Then I took out just one period separately, called it x n. So, 1 here and all zeros up to n minus 1. We carried out this DFT. The DFT is 1, because if you take the summation x n e to the power minus j 2 pi k n by capital N, this x n is 1 only for n equal to 0, when e to the power 0 is 1, and all other x values are zeros. So, 1 into 1 is the result, which is true for all k. Now, in the inverse DFT, if you put that back, okay, x k is 1. So, 1 into e to the power j 2 pi k n by capital N is x n. Small n you choose from here, fix here, and that n goes summation is over k. And now, in this formula, if you allow small n to go from minus infinity to infinity, this formula, then what you get, as we have said, is nothing but periodic repetition of that one block, which is nothing but this. So, that x tilde n, which I call sampling function, sampling sequence, that is actually can be written by this formula. Now, I start another topic, which is a big topic. I will just give some introduction to that, only very basic things I will discuss, because these are very commonplace today. This topic is called multirate DSP. I will just consider very basic things: decimation, okay, by an integer factor. So, capital M will be an integer, either at least 2 or more than 2, and there is a decimator. This is the first block, one first important component in multirate DSP. As we go into it, you will understand why we need multirate DSP. But first, let us understand some of the basic blocks. This is one block. We denote it like this, that suppose there is a sequence x n, okay, and we denote it this way. It is called decimation. And output you can give any name, I call it x d, d for decimated, x d n. It means it is like this. Suppose x n was obtained, suppose as an example, x n was obtained by sampling an analog function. Okay. There was an x a t, you had sampled here, then here, here, dot, here, and then again at this point. So, this is suppose 0, 1, 2, dot, and then this is m. This is m minus 1, okay. Then again dot, then again at 2m. So, all these 0th sample, first sample, second sample, m minus 1th sample, mth, m plus 1th, dot. This is how you sampled. But suppose I had sampled, I use a sampling rate which is m times less, that is sampling period m times larger. That is, after taking one sample here, next sample would be here then. All right. Suppose this much is your one sampling period tau. So, earlier sampling period was tau, now it will be m tau. So, 1 tau, 2 tau, 3 tau, m tau will be here, 1 tau brings to 1, 2 tau brings to 2, m tau brings to. So, now sampling period has become m tau, because sampling speed has gone down. So, instead of sampling at all these intermediate points, you will sampling here, and the next sample you will take here, next you will take here. So, now it will be 0th sample, it will be first sample, it will be second sample, like that, which means even if it is not obtained by sampling an analog signal, you have got some x 0, then x 1, dot, maybe x m minus 1, then x m, then again x m plus 1, dot, then again x 2 m, okay, dot. What we do? This is 1, this m minus 1, this is m plus 1. What we do in this process, that is, here I have drawn a general sequence, it has got nothing to do with time and all that. Maybe you generated the data yourself on a piece of paper or maybe through a computer. So, just 0th data, first data, second data. But in decimation means if you are decimating by a factor m, then after taking one sample, you discard these samples, m minus 1 samples. Then again take the next, then again discard, then again take the next, like that, which is what you are doing here. As though if you are doing sampling in the real time case, earlier you had 0th sample, first sample, second sample, m minus 1th sample, mth sample, dot 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 dot. Now you are saying, no, my sampling rate I am bringing down, sampling speed I am bringing down, which means sampling period is getting wider by a factor capital M. So, if tau was the sampling period earlier, now it is m into tau. So, after this 0, m into tau will bring you to this point, because tau brought you to number 1, then 2 tau brought you to 2, m tau will bring you to m, that will be mth sample. Previous mth sample will now be the first sample, because m tau is the new period. So, after one period you get first sample, after 2 period you get second sample. So, it is 0th sample, first sample, second sample, like that. So, intermediate fellows go, you rename these samples 0th, mth, earlier mth now becomes first, earlier 2 mth now becomes second, earlier 3 mth now becomes third, same here. x0 you keep, m minus 1 samples you throw away, then this mth you retain. So, this will be your first guy now, then again next m minus 1 samples you throw away, x2m you retain, that will be your second sample now, dot 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 dot. And this will be called a decimated sequence. Now, there is a danger, of course, you see you are bringing down sampling rate by a factor m. So, there may be a possibility of aliasing, because if the function is band limited and you must sample it at more than the Nyquist rate, okay, that is twice the band limiting frequency. Suppose you had been doing it, but now you are bringing down the sampling frequency, sampling rate here. So, there is a possibility that if you, by this bringing down a sampling rate, if you go below Nyquist rate, then you will be inviting danger, there will be aliasing. So, this you have to be careful. Maybe your Nyquist rate is less, but your actual sampling rate here, you know, that at this rate, the tau period at that rate was very high. So, you could afford to bring it down by some factor m, still remaining higher than Nyquist rate, that is okay. But by bringing down, do not bring it below Nyquist rate, then you are inviting danger in form of aliasing. This is just a word of caution. So, now xdn means xd 0th sample will be original 0th, xd first guy will be original mth, xd second guy will be original 2mth, xd minus 1th guy will be original x minus mth, because these second samples I will throw away and then I will take from minus mth, right. So, which means dot 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 dot, which means in general xd, if you take nth, it will be, if it is 2, it is 2m, if it is 1, 1m, if it is 0, 0, minus 1, minus m. So, xdn means x n mth, okay, n times m, n mth will be nth sample, mth first sample, 2 mth second sample, 3 mth third sample, n mth will be nth sample. So, this is the mathematical description, all right, xdn, and this is the notation. Then question is, given this DTFT, what is the DTFT of this? Equal to what? This will work out today. Okay, this is not an easy thing, it is a tricky thing. So, let us work out. xd e to the power j omega means by this formula xdn DTFT formula, and I am doing for DTFT, same thing you can extend to the more generalized case of Z transform, same approach. Okay. Now, you see xd 0 into e to the power 0, then xd 1 e to the power minus j omega, xd 2 e to the power minus j 2 omega, dot 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 dot, and on the left hand side xd minus 1 e to the power j omega, plus j omega, and dot 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 dot. But earlier we have seen xd 0 is same as x 0, but xd 1 is the mth original sample, first new sample, decimated sample, first sample of the decimated sequence is the mth of the original. So, I just write xm, this I keep as it is. Then xd 2, second sample of the decimated sequence is the 2 mth sample of the original sequence. Again minus 1th means originally this x, all right. Now, this omega I can write as omega by m into m. This I can write again omega by m into 2m. This I can write into m like that. Okay. So, omega is radian, omega by m also radian, you can call it omega 1. So, this is x minus m e to the power j omega 1 m, then x 0 e to the power 0, x m e to the power minus j omega 1 m, x 2 m e to the power minus j twice omega m, and dot 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 dot. See, I have to manipulate so that this term becomes closer to the original x e to the power j omega. Now, if you see x e to the power j omega, if you see x e to the power j omega, it will have x 0, but after that there is this terms, x 1 e to the power minus j omega dot 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 x m minus 1 e to the power minus j omega m minus 1, this block, then again this term. So, suppose I am carrying out it at omega 1. Okay, the x, this is DTFT at omega 1. So, next term will be, see, x 1 e to the power minus j omega 1, x 2 e to the power minus j 2 omega 2. This is the original DTFT, and this, then x m e to the power minus j omega 1 m, which is present here. Then again there will be terms, x 2 m, sorry, x m plus 1 e to the power minus j omega 1 m plus 1, again dot 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 some term, and again this term will be present. These are not present here. These are not present here. Okay, only this is present, this will be present, like that. So, this summation, this DTFT is part of original DTFT at a frequency omega 1, where omega 1 is this, omega 1 is this. So, original DTFT at omega 1 has got, it is a generalized expression. This has got the terms present in this DTFT, they are plus additional terms. Okay. Now, if I can make this additional terms 0 in the original DTFT, then I will get this, that will become equal to the desired DTFT, this x d to the power j omega. For this, what I do is this. Suppose this is your original x n, mth sample, 0th sample, intermediate samples I am not so bothered about, again these intermediate samples, then x 2 mth. On this side also you have got something, then x minus mth dot 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 dot. This is the original sequence x n, right. Suppose I multiply it by that sampling sequence I told you, 1 0 0 0, then again at mth point 1 0 0 0, then again at 2 mth point 1 0 0 0, then 0 0 0 0 0 at minus m 1 dot dot dot. If I multiply by the 2, okay, let me call it S n, sampling sequence. So, x n into S n, suppose I do, then what will I get? I will get x 0 into 1, and then these fellows will give rise to zeros, this into 0 is 0, this into 0 is 0, this into 0 is 0, then x m into 1, so like that. So, this will be like the decimated sequence x 0, but in the decimated sequence this fellow x m was called first sample, it was index 1, but now these zeros I have brought back. So, it will be mth again, x m into 1 So, ms sample will be xm. This into 0, 0, this into 0, 0. So, m minus 1 zeros and xm, again 0, 0, 0, m minus 1 zeros, x 2 m, dot dot dot, again m minus 1 zeros, x minus m, right. If I take DTFT of this sequence at omega equal to omega 1, what will I get? X 0 as it is plus 0 into something, 0 into something, they do not contribute anything. So, next is x m, so x 0, then these zeros we forget, then next is x capital M, at capital mth point, so it will be minus j frequency omega 1 m, then again zeros we forget, next is x 2 m e to the power minus j omega 1 into 2 m, and dot 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 on this side these zeros we forget, next x minus m e to the power minus minus plus, so j omega 1 m, and dot dot dot, and this is what you have here. You see, x minus m e to the power j omega 1 m, x 0, x 0, x m e to the power minus j omega 1 m, x 2 m e to the power minus j 2 omega m, 2. Okay, this 2 omega 1 and omega 1 2 is the same thing. So, this DTFT of the decimated sequence is same as DTFT of the product of these two original sequence multiplied by the sampling sequence at a frequency omega 1. Remember, this DTFT was at a frequency omega. So, decimated sequence is DTFT at a frequency omega, it is same as DTFT of this product sequence xn Sn, xn was the original sequence, Sn is the sampling sequence, so xn Sn at omega 1, where omega 1 is omega by m. Okay. That is, decimated sequence is DTFT at any this is DTFT of xn Sn at omega 1 equal to omega by m. All right, the two expressions are same. All right. So, this we work out. We try to carry out DTFT of this for this choice of omega 1. All right. That means x d e to the power j omega, by this expression it means the product x n S n e to the power minus j omega 1, because at omega 1 is the frequency where you have to find out this and omega DTFT. Now, S n, I told you the sampling sequence can be represented in this manner. Just a minute. That time it was called x, now this is called s. It was called x tilde that time, the same thing I am calling S n now. The S n can be represented like this. So, that I substitute here, this S n I replaced by that, 1 by capital N will go out, outer summation as before, x n S n, so summation k equal to 0 to n minus 1 e to the power j 2 pi, that k from here, n from outside, and then multiplied by e to the power minus j omega 1 n. All right. And now, this we can simplify. Whenever I know that whenever there is a double summation, next step is to interchange the two summations. So, this summation over k will go out. N from minus infinity to infinity. X n e to the power minus j. Now, omega 1 I replace by omega by m. Okay. Now, this is not n, this will be m, sorry, I forgot to mention, because it was here the period was taken to be capital N, 0 to n minus 1, but for our business For our business, it was this m, right. Just give me a minute. Yeah, here this is a sampling sequence. Earlier I took 0 to 0 and then capital N, 2n, 3m, that is m, capital M, 2m. So, that is why in this formula I should not write n, it should be m. Okay, it should be m, everywhere it should be m. And omega 1 I know is omega 1 is omega by m. So, now here I write x n e to the power minus j, I take this common, not omega 1, omega by m. So, omega minus n I will put outside 2 pi k by m into n. Omega by m is omega 1 into n with minus e to the power minus j omega 1 n, that is present, and another term is minus minus plus j 2 pi k small n by m all right. Now, what is this summation? Omega is radian, digital frequency, minus 2 pi into k another radian. So, omega minus 2 pi k is radian, another digital frequency, divided by m still radian, this is another digital frequency. If you call omega prime, so this is nothing but this inner summation is what? Summation x n e to the power minus j omega prime n, all right, which is nothing but DTFT at omega prime. So, x e to the power j omega prime. So, this entire thing then turns out to be this x d e to the power j omega is 1 by capital N this much frequency omega prime. Instead of writing omega prime, I am writing this full form. Okay. So, this is the DTFT. Now, what is the interpretation of this? For that, we will take an example. Okay. I do not know whether I have that much time today, but nevertheless, we will take an example of just m equal to 2. Okay. And suppose I take a fresh page. Suppose this formula I need. Suppose what is given is x e to the power j omega. Again I tell you, you cannot plot a complex function by just one plot. I should have mod of this versus omega and angle of this versus omega, but just to explain my point, I am ignoring that. I am plotting capital X to the power j omega versus omega. Suppose this is given to you. Like this. Okay. Now, this x n that has this DTFT, and this x n I am decimating by a factor 2 to get x d n, that is m equal to 2. Question is, what will be this x d e to the power j omega? That by this formula will be 1 by n, sorry, it is not n, it is m, everywhere I am making the mistake. There is no capital N here, it is M. Okay. Let me correct. This should have been M. Huh? So, now this summation means 1 by m, m is 2. So, 1 by 2 and there will be only two cases, k equal to 0 and this is m. Again here this should be m. Wherever you had n, that becomes m, okay, m minus 1. Sorry for this mistake. Okay. There is no capital N, for our notation here this is all capital M. So, instead of capital N, everywhere it will become capital M. Okay, that is why it is capital M, capital M, capital M. Half k equal to 0 and m2 means there is 1. So, 0 case and 1 case. If you put k equal to 0 here, you have got x e to the power j omega by 2 because m is 2 and then x e to the power j omega minus 2 pi into 1 because k is 1 now, if m is 2. All right. If you plot this, then we will get that. This we will do in the next class. You can see one thing, if you look at this DTFT, pi corresponds to, as I told you, half sampling frequency. This is the analog, this is the digital version of the analog band limiting frequency. So, here half sampling frequency itself is twice the band limiting frequency, whereas to avoid aliasing it was enough if band limiting frequency is equal to half sampling frequency. So, that means I can still bring down the sampling rate. Half sampling frequency is pi, is giving analog half sampling frequency going to pi, analog band limiting frequency going to pi by 2. So, I am finding half sampling frequency is already twice, okay, the band limiting frequency, which is not required. Half sampling frequency could be equal to band limiting frequency. The band limiting frequency is fixed. So, I can bring down the half sampling frequency and therefore sampling frequency by factor 2. So, in that case half sampling frequency is always analog half sampling frequency will always map to pi. So, band limiting frequency will go like this, then they will coincide with that and it will be like that. This we will see in the next class. Thank you very much. You try this as an exercise by yourself. Okay, we will meet in the next class. Thank you very much.